In this lesson, we'll overview the ideas of variance and standard deviation for random variables with a specified probability mass function and for random variables that are defined as functions of those random variables. Well, let's begin by talking about moments for a random variable. The first moment for a random variable is simply the expected value for the random variable. The second moment for a random variable is the expected value for the square of the random variable. The third moment, expected value for the third power of the random variable. And in general, the nth moment is the expected value for the nth power of the random variable. Now, the first moment for the random variable is called the mean, or the expected value for the random variable, and we use this moment to specify the average value for that random variable. The second moment for the random variable is sometimes called the average power, because the physical concept of power is often associated with the square of some physical quantity. As we said earlier, the mean for a random variable is simply the expected value for that random variable, and we often use the Greek letter mu to denote the mean for a random variable. And here we've included a subscript x to show that mu represents the mean for the random variable, called x. Now, the variance for the random variable is sometimes called the second moment about the mean. That is, we subtract the mean from the random variable and then evaluate its second moment. Now, this important expectation represents a measure of the variability of the random variable, and we often use the Greek letter sigma with a superscript 2 to denote the variance. Now, as we did with the mean, we've included a subscript x to show that this is the variance for the random variable x. Now, with a little manipulation, you can show that the variance is also equal to the second moment for the random variable minus the mean squared, or the square of the first moment. Now, this relationship, which might be written like this, shows that the mean, the variance, and the second moment only have 2 degrees of freedom. That is, if you specify 2 of them, then the other one is also specified. Now, I suppose if you specify the second moment and the variance, then we'll only know the square of the mean. Now, because the variance must be greater than or equal to 0, the second moment for a random variable must always be greater than or equal to the square of its first moment, or its mean. Finally, the square root of the variance is called the standard deviation, and that's usually denoted by the Greek letter sigma, which is why we define the variance to begin with as sigma squared. The standard deviation is an important measure of the variability of a random variable because it has the same units as the random variable. And as a qualitative rule of thumb, we might say that a realization of a random variable that is within 1 standard deviation of the mean is common, but a realization of a random variable that is more than 3 standard deviations from the mean is uncommon. Now, for specific situations, we can be much more quantitative and precise about those relationships. Well, let's look at a discrete random variable that counts the number of independent Bernoulli trials until the first success, when each trial has a success probability equal to alpha. This is a version of a random variable that's called a geometric random variable. Now, we can derive the probability mass function for this random variable by noting that if the first success is on the nth trial, then the first n-1 trials must be failures with probability 1 minus alpha, and the final success has a probability of alpha. Now, the mean for this random variable is the sum of each value in the range, which is the positive integers from 1 to infinity, times the probability that the random variable takes each of those values, which is determined by the probability mass function. The second moment for the random variable is the sum of the squares of each value that the random variable can take in its range, times the probability that it takes those values. Now, at this point, we can substitute the probability mass function into each of these summations and derive an expression for each of the expected values, the first and second moments. Now, rather than work those out by hand, I've chosen to utilize the symbolic tool Mathematica. Well, to begin with, I've defined the geometric probability mass function as a function of the variable k that I'll use in the summations, alpha times 1 minus alpha to the k minus 1. Then I can evaluate the first moment, or what I'm calling mu x, as the sum of k times the probability mass function evaluated at each of those values from 1 to infinity. The second moment, very similar, with now the summation of k squared times the probability mass function at each of those values. Once I've computed those, I can ask Mathematica to display them for me in fully simplified form, and I find that mu x, or the mean, is 1 over alpha, and the expected value of x squared, or the second moment, is 2 minus alpha over alpha squared. Now from those, I can also get an expression for the variance, and the corresponding standard deviation would be the square root of that. As another example, let's suppose we have a Poisson random variable with a mean parameter of lambda. And furthermore, let's assume that another random variable y is equal to some constant b raised to the value of x. Again, using Mathematica, I can begin by setting up the probability mass function e to the negative lambda, lambda raised to the n, divided by the factorial of n. And then I'll transform n to a variable I'll call y by raising b to the power of n. And that corresponds to the values that y takes for every value x could take. The expected value for y, then, is the sum of all of the values that y takes for each index in the range for x times the probability that x takes those values, and then we sum over the range. Second moment, we do the same with y squared, and then the variance is the second moment minus the first moment squared. Then if I want to see each of those expressions for the mean, the second moment, and the variance, I find that the mean is e to the power of, well, b minus 1 times lambda. The second moment is e to the b squared minus 1 times lambda. And then, of course, the variance is the second moment minus the first moment squared. Well, in summary, whether we need to determine the first and second moments for a random variable or for another random variable that is a function of a random variable, we'll always be able to define those moments as familiar sums that involve the probability mass function for the original random variable.